So actually, both Jacob, who's our director of product, and I are on Capitol Hill today, meeting with a few offices and wishing people happy holidays. But yeah, that video, we didn't actually have a Horace and Paul Revere driving through the halls of Congress, as some people seem to think. That was just AI and a testament to the team's ability to generate some pretty cool content. But yeah, just want to thank everyone for being here and sort of set the scene really quickly. I know a lot of people understand what casework is here. They've either done it or they're adjacent to casework. But for those who aren't familiar, casework is really the government and Capitol Hill state local offices working to provide solutions to constituents. So it's kind of what we consider the other half of the equation, where a lot of civic is about policy and detecting policy trends and demands from constituents. Casework is the side of actually delivering solutions. For example, someone missing their social security payment or having a problem with a state or local agency. Casework through their elected official is the way to get some resolution there. And so that's what this is. That's the core of this and what this is about. And we've got a great team from Smith College. I'll let them introduce themselves and get into their work. But I really quickly want to turn it over to Megan Blackwood, who is our casework product manager and advisor at Civic, to just maybe give a minute or two about her work and the importance of casework and what we're doing here.
Guys, yeah, John, great lead in, right? You covered most of the big stuff, but for a lot of people, they don't really know about casework or constituent services, and it's definitely probably the less sexy side of what happens in Washington on the Hill. But it really is, I believe, and I'm pushing forward with my academia, the biggest way that elected officials can serve members of the public. Really just stepping in and being an advocate for them in really everyday situations, right? We've all had trouble with our mail. Any of us that have issues, have any direct connection to the government through services and stuff, could probably tell you about all the red tape they experience. So this is just a way for members to step in and serve their constituents in this way. And what we've had the team from Smith working on is so important because when we do look at these services, a lot of the stuff that slows it down is that triage, figuring out the case, figuring out what it's about, who's the best person to handle it, what's the agency contact. And that's really where we're trying to step in with some of this AI technology to be able to batch some of those information, batch those letters faster, get them to caseworkers so they can start doing the important work of advocating and intervening for constituents with the federal government. I think that's it.
Thank you. Should
Should I throw it over? Well, then look, I'm going to take this. I'm going to take the rest of my 2 minutes to throw it over to the team at Smith. We have had an amazing experience working with them this semester. They were curious, they were driven, and they weren't afraid to push boundaries and push the project in a way that made it really more than we could even imagine when we started. Julian and I have both just had an amazing time working with them this semester. And I'm going to go ahead and let them take it away and start showing you guys some of the amazing work that they've been doing that will eventually help caseworkers repair American democracy.
Thank you so much for the intro. Okay. So what we're going to be talking about today is using classification models to make casework easier for legislative aides. So we'll go over a team introduction, the background of our project, how we implemented a model, and then future feature development, and a conclusion and discussion. So to introduce us, we're a team of undergrads from Smith College studying statistical and data sciences. And we've had the opportunity this semester to intern for Civic as a part of our senior capstone project.
And a quick introduction, I'm Kate.
I'm Gabriela.
I'm Robbie.
I'm Yuzhang.
And I'm Anabel. So for our project background,
We were working on legislative casework. So this is when constituents send emails containing information about difficulty navigating government programs, whether that be having trouble filling out immigration paperwork, or my property was destroyed in a storm, and I'm wondering if the government has anything that they can do about it. So they send these emails to their legislative offices. And then in the offices, aides are tasked with determining which government programs would be most useful to the constituent. So the problem that we were looking at was, how can we make this process more efficient for legislative aides? And some of the things that we thought about needing in order to solve this problem are being able to organize the many governmental agencies, programs, and issue areas using a tiering system, generating a large data set of realistic synthetic emails that could potentially be sent to legislative aides. And the reason that we want to do synthetic emails is that we would have privacy concerns using real emails. And then create a model that would assign tags to incoming emails according to this tiering system.
All right, so just a quick introduction to what the CAO casework tiering system looks like. And I'll just say, if there's anything that's not clear, please feel free to ask a question about our process and like our explanations. The Office of the Chief Administrative Officer in the House introduced this year a unified tagging system, which caseworkers had been calling for a while, to standardize the labels that congressional staffers are using to record casework. This is important for two main reasons. One is data aggregation, which we as data scientists are really interested in, understanding policy failures as broad issues that are systemic rather than individual problems with a specific program, that having a unified tagging system allows us to understand much more clearly. And then the secondary service that this tagging system provides, which is more in line with our project, is that it increases the efficiency of the system by rendering the tiering system more consistent across caseworkers and offices. So people are more able to communicate across different branches of government with each other. So just a bit of an intro into how the system actually works, and a note that these examples and explanations come from Megan's article toward a unifying tagging system for casework in the US House of Representatives. Tier 1 is the overarching organization of government that the program falls under. So that would be like Health and Human Services or the EEOC. Whereas Tier 2 is a sub-agency that's nested within that. So like the Center for Medicaid and Medicare Services. And there are 44 Tier 1 bodies and 66 Tier 2 sub-agencies. Tier 3 is the specific program level at the Tier 2 sub-agencies. So like Medicare Part A, GI Bill. And Tier 4 breaks organizations down into their program-specific departments and incorporates insights about recurring program-level problems revealed through CAO's ongoing partnership with caseworkers. And this tiering system is important for us because it's both what our model is trying to cluster messages into, sort them to be able to tell caseworkers this is what this is referring to, and also was a scaffolding for how we went about generating synthetic messages, because there was a lot of information in the tiering system about what specific programs were in service of that was really helpful as we were generating messages.
And next, let's step into the project roadmap part. So this slide shows the overall workflow of our project from data generation to model analysis. We start by generating a large number of synthetic messages through prompt engineering. This allows us to protect database privacy and also explore the task under a broader range of realistic language. In the dataset, the message column contains raw text, and there are multiple label columns such as top agency, issue area, etc. Next, we convert all of the messages into semantic representations using text embedding models. We began by conducting a train validation test split to the dataset to avoid information leakage. And then each message is mapped into a normalized embedding, placing all text into a shared semantic space where similarity reflects the meaning. And once embeddings are fixed, oops, sorry. Once embeddings are fixed, we experiment with different inference strategies, such as centroids and Bayesian approaches. These methods use a training set to define decision rules in the embedding space and also the validation set to tune or compare strategies. We then compare the model performance using F1 score matrix, both at the overall level and also across different label categories. These allow us to evaluate not only accuracy, but also how well the model balances precision and recall across classes. Finally, we perform analysis by examining patterns in incorrect predictions. Insights from these errors guide the design of new strategies, which are then fed back into the training and inference steps, forming an iterative improving loop.
All right, so let's first go into more details about the data generation part of our pipeline. So as Anabel mentioned earlier, for privacy issues and also for the fact that we don't have enough real emails to train our model on, we started by generating a bit more than 10,000 emails to work with Titan Text Express. This allowed us to create a data set of semi-realistic emails that is evenly distributed across issue areas and top agencies. So the data generation pipeline consists of 5 basic steps. The first one is to select a tag set for that represent a casework issue. This tag set will follow a hierarchy that goes from top agency to sub-agency to a program title and then the associated issue area that goes with this casework. So just before just before we select a tag set, we want to make sure that all of the tags we use are meaningful and helpful towards classification later. This is done by applying a set of domain-informed filtering rules where we will drop overly specific tags or tags that has to do with a specific year or a one-time disaster relief programs, while we also make sure that we include all of the core casework categories. That's about healthcare, immigration, and employment. And then we also apply proportional sampling, where we will make sure that all the top agencies are equally represented in our data set. So because each tag set will later on produce 27 variations, a total of 10,000 emails would mean that we need around 400 sample tags for the data set. So this step simply means that we make sure that after we're done with generating, we have approximately the same number of emails in each top agency, as you can see from this distribution table. And then on to step 2, we will then insert this tag set into a prompt that also take a persona profile that has 3 levels of trust, efficacy, and knowledge. 27 variations, as I just mentioned. And then we also engineered this prompt to enforce consistent structure, length, tone. We strictly ban any reference of the tier labels. And then we also add realistic names, dates, and other email information to make the messages feel more authentic. And then after we're done generating all of the emails, they will go through a quality control step where we flag and remove all the messages that contain weird characters, model refusal text, leftover placeholders, prompt leaks, tag leaks, things like that. And then all of the tag sets that failed quality control will go through a regeneration step where we reuse the same prompt again and allow for multiple retries so that we can maintain a total of 10,000 emails. So we have put here a sample email that was generated with Titan Text. It reads, "Dear Senator, I'm writing to urge you to provide $400 million in funding for the Social Services and Income Maintenance Benefits Enrollment Coordination Grants Program." That's a very long name. In the FY24 budget, this program supports community pilot projects that provide benefits outreach and enrollment assistance to low-income and individuals and families. Thank you for your time and consideration of this important issue. So as you can see, this email should go to Departments of Health and Human Services with concerns about income and employment.
So next, once we've done it with the data generation part, we first translate the text into the numbers that can capture the meaning. So the computer can compare the text based on what they are about. So an embedding turns each piece of text into a point in a high dimensional space where text with similar meanings are closer together. So on the right, here is a diagram explaining the process of creating text embeddings. As we can see from left to right, words are turned into a series of numbers which form vectors. If we apply dimensionality reduction and map these vectors into a 2D space, we can see that words with similar meanings are closer to each other. For example, in the top plot, cat and kitten are the closest 2 points. Dog is slightly further away, while house is far away from all of these 3 points. So the closeness of these embeddings successfully reflects the semantic relationship of these words in real life. The model we use to realize this step is the Titan embedding model version 2. So each text embedding has a dimension of 1024. We normalize the embeddings so that all texts are compared on the same scale. This ensures that the model focuses on meaning rather than the noise. By working with positions in a semantic space, we're able to test different ways of grouping and classifying the text. So this step allows us to turn unstructured text into something measurable and comparable under a global semantic context. So once the text is embedded, classification becomes a question of proximity. Which group is this text closest to? So at this point, each text has already turned into a point in this space. For start, we have chose the centroid inference approach. The key idea of this method is that for each category, we compute an average location that is a centroid that represents the group in the semantic space, using all of the simple belonging to that category in the training sets. And during the inference process, for each new message, we calculate the similarity between its embedding and the centroids of all categories respectively. That is the distance between all of these points. We then assign the category whose centroid is closest to the point, representing the new message as the prediction results. So in this way, classification becomes turned into a nearest center problem in this space. So the advantage of this approach as a baseline includes there is no complex parameters. It is less prone to overfitting, and also it provides a simple and interpretable way to classify the text. So on the left, here is a T-SNE plot that projects the high dimensional embedding into a 2D space, while also preserving the local neighborhood structure. So from the plot, we can see that text belonging to the same category tends to form clusters, while different categories are separated to varying degrees. Each color corresponds to a category, and its center roughly reflects the centroid used for inference. So this visualization provides an intuitive explanation of why centroid-based approach works. Then to evaluate how well our classification perform, we use F1 score that integrate precision and recall, which describe different aspects of the model behavior. So from this pic in the right, say each dot represent a message. The shaded area shows the message that are truly belong to a category, and the circle shows that the messages model predict as a category. The overlapping part shows true positive, like the left half side of the circle. And points inside the circle but outside the shaded area are false positive, and points inside the shaded area but outside the circle are false negatives. Precision basically answers the question of all messages the model predicted as belonging to this category, how many are actually correct. So a high precision generally means that when the model assigns a category to a message, it is usually correct. On the other hand, recall answer a different question. Of all of the messages that truly belong to this category, how many did the model correctly identify? So a high recall means the model is good at capturing most messages from this category, even if sometimes the model assigned the category to extra messages. So together, precision and recall capture a trade-off between being accurate and being comprehensive. In our context, these metrics help us understand not only whether our models are making correct predictions, but also whether it is missing important messages. And one extra note is to make sure we're making apples to apples comparison, we have maintain our random seed and also the same split for all of the inference approach that we have applied. And then here is a screenshot we have from the baseline approach. So looking at the F1 score over here, where macro F1 score stands for the general F1 score, and the weighted one is weighted by the frequency of the frequency of each label. We have really close similar metrics, which is 0.67 as our baseline metrics. And next, we're gonna talk about how we use feature development to improve our model performances.
Yeah, so 0.67 isn't bad, but we wanted to do better. And so we came to the idea of using contrastive learning, thank you, Julian, where we wanted to move from the image that we have on the left-hand side, where all of our clusters are a little bit too spread out for our liking, and we wanted to get to the right-hand side, which is the result of this reduced vector space, so reduced embedding space, that makes the inference of the casework a little bit easier, just because the messages are grouped more neatly into their agencies. And so for the contrastive learning part, the idea is that if two messages are similar to each other, you should distort the embedding space so that they are moved closer to each other. And if two messages are different from each other, therefore like from different agencies, to make sure to move them further apart. And so we defined a PyTorch model where we used the backbone, the frozen Titan embedding. So the one that gave us our baseline 0.67 accuracy. We used that and we applied a projection head. So a two-layer multi-layer perceptron, also called a feed-forward neural network, that has two linear transformations with an activation function in between. So if we look on the left-hand side, we see that the yellow box, we start with the original Titan embedding that has 1024 dimensions. We apply a first linear layer, and the idea is keep the dimensions, but change the geometry of it, so allow skewing the vector space. Then you apply the activation layer that adds nonlinearity, so the model can learn on nonlinear transformations, which is very important for separating classes in supervised contrastive learning. And then we get to the third linear layer that reduces the dimensional space from 1024 to 128 dimensions. The idea is to get rid of all the noise, so to really just keep the most important dimensions. And in the literature, it's quite common to see 128 as the chosen final dimension. And this is more contrastive friendly, and that's what we ended up using for our projection head. And so once we applied these, like transformations, we wanted to train our model, and we did 10 epochs. So one epoch is one full pass through the entire training data set. And each time the model goes through the data, it improves the embedding space. And so the idea is that the loss function gets closer and closer to zero. This is a mathematical property because the loss function is the negative logarithm of like this ratio of what's similar and what's different in your embedding space. But the idea is the closer you are to zero, the better your model was trained. So it took us about 10 epochs to get pretty close to zero. And This really was quite productive because it increased our accuracy to our overall accuracy to 0.82, and we see it's quite constant and in between agencies too. So we're looking at the F1 score that Yuzhang also just explained. So 0.82 was pretty good, but we were curious what else we could do to maybe increase it.
So the next thing that we tried is that we were wondering whether we could improve the model by changing the syntax of the emails. So we decided to try text preprocessing. So text preprocessing takes our synthetic emails, again, does the and then changes the syntax of the emails. So whether that be removing words that don't have too much meaning, like the or is, or removing punctuation. So then we perform those changes and then do our same train, test, and validation split, generate the embeddings for all messages, and then fit our contrasted model using the new training embeddings and run our new model using our new test embeddings. And then, of course, finding metrics for our predicted labels. So we decided to test out 6 different methods for text preprocessing on a subset of our data. So we have our raw text, the removal of punctuation, removal of the, is, and a, removal of standalone letters like I, a, and any other sort of random characters that show up, and then a removal of a list of about 200 stop words. And then our final one was stemming, which is reducing our reducing words to their most simplest form, like taking the word writing and changing it to write. So on the smaller subset of our data, we actually found that our metrics decreased for all of the strategies except for the removal of punctuation, which increased a little bit. So then we decided to test the removal of punctuation on our full data set. And what we found is that it actually decreased our F1 score, meaning that text preprocessing is not a useful step in our model. One of our theories is that it's possible that the Titan embedding model that we use is sophisticated enough to pick up on the new nuances in the language, like punctuation and stop words, to make it so that every single part of the email actually is useful. So we decided to take this information and scrap our whole text preprocessing idea altogether.
So in the end, as a wrap up of what we've done throughout this project, here is an updated version of the diagram we have. So again, we start from creating the synthesized dataset. We applied the train test split. We took them into the text embedding model, and we applied supervised contrastive learning to get the remapped embeddings. And then we have tests the embeddings on different inference approach, such as centroids, Bayesian, and KNN, and they're evaluated using the F1 score. In the end, we still choose to use centroids model as our final dataset. And over here, this is the improvement of our metrics from 0.67 to 0.82. And then last but not the least, we decided to take a look at all of these incorrect errors that the models made and what can we learn from them.
Yeah, so as Yuzhang said, we were really happy with the metrics that we were able to generate on the tier 1 agencies, but we wanted to do a little bit of error analysis to understand where the remaining error was coming from for whoever takes on this project moving forward. So basically, we wanted to understand, are these errors coming down to randomness, or is there some systemic issue in either our model or our data or a complexity of the problem that we weren't taking into account when we were fitting our model in the first place, that moving forward could help future researchers boost the metrics even further. So after doing the error analysis, basically looked like taking a random sample of the messages that had been misclassified, looking what were they really, like what department did they really belong to, what were they classified as, and then reading the message itself to identify if it was an issue that a human annotator also could have had. And basically, in reading these messages, we discovered four main problems. The first was synthetic message problems. Then some agencies in the data set have natural overlap that a human annotator could also make mistakes with. There are some topics that span multiple agencies, and all of the messages used very generic assistance-seeking language that confused the model. So just for some examples, there was some vague sample messages that didn't make reference to any agency, or errors in how our synthetic data was generated that slipped through the quality control that we had in place. And what this tells us is that some of the error is not due to a weakness in the model itself, but rather in the data that we used. And so we wouldn't expect it to affect the model's performance in the real world. The second issue that we identified is that some agencies have natural overlap, and that might be exacerbated by the fact that constituents don't always know exactly what they are asking a question about when they reach out to their legislators. So some pairs that were commonly mistaken for each other were the Department of Homeland Security and the Department of Labor, which makes sense because those messages were making reference to employment authorization, work documentation, and status updates, which either agency could be handling issues where those keywords are being used to describe the problem. Department of Defense and Department of State, also a similar issue. The Small Business Administration and the Treasury, the Department of State and Homeland Security, Department of Health and Human Services, and the Department of Labor. So these reflect label ambiguity that's inherent in the problem, not necessarily our model doing a bad job. So that could, and notably are issues that human annotators might also make mistakes with. And so that is something to bear in mind going forward with this model is having associated like confidence levels with specific predictions, because there are just going to be certain pairs that are really difficult to distinguish between and might need a human pair of eyes going over. The third issue was multi-agency topics, which basically the way that we designed our model constrained the model to predict a specific agency. And there are some issues that a constituent might have that multiple agencies might need to be in contact with each other to properly solve. And so like education abroad was one that came up a couple times in the synthetic messages that I noticed. And these reflect the fact that this problem is really complicated. Again, not necessarily model weakness, but something that future researchers should look into, having a model that can predict multiple agencies. And the fourth and final issue was that the model is overweighing generic assistance-seeking phrasing rather than relying and underweighing the domain-specific cues that might differentiate between agencies. And so a lot of these messages are like, "Dear Congressman, I would like an update about this. Can you please follow up on my case about this?" And if the model is reading all of the words in the message as similarly important, that's a lot of noise that's flooding the system. And so that is something going forward that people should take into account. Finally.
Okay. So to put our model back into context, we initially envisioned it as a tool to surface the most relevant agencies or programs for an incoming constituent email, to also identify common bottlenecks that they are facing, and also to allow for further analytics on the issue trends in a certain office. And we think that this model can be further improved by, first of all, experimenting with other domain-specific embedding models. Right now, our model only identifies the most relevant top agency. Further iterations, we could push this accuracy further by also predicting the specific sub-agency and the exact program that this email can be directed to. And this combined with confidence level-based routing, like Gabriela just mentioned, we may expect much higher accuracy and efficiency with this model. And then when available, we can also incorporate anonymized or semi-real constituent emails and maybe further expand synthetic email generation to account for more realistic writing styles and tier imbalance. So this is the end of our presentation. Thank you so much for paying attention. Before we move on to questions, we want to give a big shout out to Julian, Megan, and John at Civic for your constant support. We also want to thank our Professor Nico Stevens and our classmates in SCS 410 for their help and feedback. So if you have any questions, feel free to ask away or put it in the chat. Thank you for listening. Aw. We stop sharing. How do we stop sharing? Okay. Thank you, guys.
Great job, guys. Did anybody have any questions for the team before we get out of here? We want to give you guys a chance to ask anything you might want to. I knew they threw a lot at you.
A whole semester's worth of work.
Does anyone have any suggestions of where they might have improved the
Wait, I have a question. I really like that you guys kind of like were forward thinking in terms of like how are you going how like if somebody was going to pick this up after you, how could you like do a better job? But I think another interesting area would be to like kind of like tweak the problem space a little bit because like you guys talked about in the beginning how you kind of ignored single issue. So it's like single issue tasks. So that's like if a hurricane happens and like all the tasks related to that. Well, although I think what might be like an interesting extension though would be to the like if you have this classification that like of all these emails coming in for a hurricane, but like there's many different things that people need like in terms of food, in terms of housing, in terms of understanding if their loved ones are okay, stuff like that. If you're going to like try and ingest those types of emails, how do you think you like how would you go about maybe like if you're going to continue on this? Do you have any ideas of like how you would like continue? To like work on that type of like specific sub problem.
So, one particularity about the messages generated, for example, for Hurricane Katrina, is that there were government programs that were particular only to Hurricane Katrina. So it wasn't just about like general questions about food, but it was a government program that literally like in the way that the labels and the tags were made when we generated the messages, we generated them to be specific to that, and therefore the classification would only happen with the data that we have and therefore with the labels that those messages had. So the reason that we removed that is because we won't have a Hurricane Katrina again, that it's in the past. So the very specific examples that were of the past, we decided to remove. But I think it would be interesting if we were to manually go over those messages that were generated and reassign them a label and say, actually, you're not just about Hurricane Katrina, you are about, like, say, food regarding a different government program, to then see how the model would learn and maybe improve.
I think that also that kind of, we didn't get into the like lower tier classifications much, but we had like discussions about how you would go through breaking these like larger agencies into smaller tiers in a clustering model. And I think that that is like reflective of a similar question about the problem space of like, do we want to have this main model that breaks everything into clusters and then feed like, do we want the model to know that those clusters are tiered within each other? And I think that the hurricane example, as Kate said, like is difficult because it sort of stands apart from the like, how would you say that? Like
The nested tier.
The like hierarchical nature of the problem because it is sort of standalone. So that's why we decided not to take that data into our model, as Kate said. But I think that it would be interesting. It does like change the problem space significantly in a way that makes it like hard to know how to create a unified model that addresses all of that.
Awesome. All right, yeah, thanks.
And in terms of tagging, I think maybe one solution to your question would be to have multiple tags per email, and maybe in that case, instead of just taking the tag that was closest to an embedding, sort of having a threshold, like any tags that are within this threshold could be used as
Yeah.
the tag. Yeah.
Yeah, and then probably applying some more conditional functions to it. So if
Yeah.
like say the second tag is actually the one that's right, the second nearest centroid, so to say, is actually the correct label, then the idea would also be if you contain certain keywords, right, and you are the second closest one, actually that might be your correct tag. So I think there's lots of room to improve and play around.
Does anyone else have a question?
Hey team, I have a question. First of all, good to see you all again.
Yeah.
Really great to see where this project ended up. I think it's really creative and good work that you did. So you should be really happy with yourselves.
By the
So-
way, Mike here is a data science PhD at the Advanced Research Division. I don't know if I got that right at NASA. He contributed to the ideas around applying Bayesian inference to the project. But yeah, would love to hear a little bit about that as well, Mike, maybe after you ask your question.
Sure. Yeah. Well, I mean, I was kind of curious about how that part turned out. But my original question was about the embeddings. So there are obviously a bunch of different, I guess, embedding tools out there or algorithms out there. I was just curious why you picked the Amazon one, or if you had tried different ones, and like, did the Amazon one perform the best? Like, what was the thinking behind that?
So as we just mentioned, there are a lot of rooms for us to experiment and to play, and that is even larger room at the beginning of this project. So it's actually just very simple reason that we are recommended by Julian to first take a look at the AWS models. So we think Titan embedding model is a good choice, and we spent most of the time throughout the semester on experimenting other approaches. So we actually did not try any other text embedding model yet. But we are aware of there are a lot of other choices and options, and there are even the model that integrate the generation of embedding and the inference part together. So that would be actually one of the others, or like one of the other possible development for the next semester for development in the future.
Yeah, and just quickly about the Bayesian stuff, we did do the Bayesian experiments, and they did help with the accuracy scores pretty significantly. But then once we did contrastive learning, it improved everything by so much, and then the effect of Bayesian was very minimal.
Okay.
That is why we didn't end up like including that in the presentation, because it wasn't part of the final model. But it was cool for me personally to like learn more about Bayesian stuff and figure it out.
Yeah, well, some say it's the future. I mean, I think that's a little heavy-handed, but it is very cool. And I did like the contrastive learning thing. I thought that seemed very sophisticated and interesting. So that seemed like a really good choice. So yeah, great job again, everyone. It was really fun to
Thank you,
listen to this.
Julian, for pointing us towards
Contrastive
contrastive
learning,
learning.
yeah.
Does anyone have any other questions that you need further clarification on?
And for the questions that show up in the discussion section, I have typed out the name. It's Amazon Titan Embedding Model version 2.
Sorry, I wasn't referring to the embedding model that was used, but I don't know if I just caught it wrong. I'm also kind of multitasking. I apologize. But you had mentioned that you were going to experiment with a model that does both embedding and inference. Which model is that?
So I might be incorrect because I haven't done much research on this type of problem yet. But if I'm remembering correctly, I can think of BERT, the model.
Oh yeah, the
And
art topic.
Yes. And also some other models under the PyTorch framework.
But I think our answers were very much referring to like Google searches, but nothing that we fully explored yet. So we might be incorrect.
Yeah.
Okay, yeah, because I think they're like, I'm sorry, I should have introduced myself. My name's Akil. I'm a specialist solutions architect at Amazon that's focused on generative AI. So great job using Titan. Appreciate it. But yeah, I was just curious because I haven't found one that combines both embedding inference because they essentially operate as two distinct paradigms. But awesome job. This is super cool.
Thank you.
Thank you.
I'll wait another moment to see if anyone else has a question, then I'll pose another question. Could you go back to the slide with the spatial mapping of the embeddings, or the visualization of the embeddings?
Yeah.
The contrastive learning one?
Yeah.
TNC. Okay. Let's see. And sharing.
This one?
Yep. I'm wondering, was there any error analysis done or investigation of the centroids that are still, or sorry, the clusters that are still kind of overlapping on the right?
Yeah, so we didn't include the confusion matrix that we had generated earlier in this presentation, but a lot of the space in the very middle of this plot, like, okay, so basically we looked at like which pairs of agencies are getting misclassified as each other most frequently, and we were able to determine some patterns, but not a like overarching, very significant bias or error. And so I think that those that are in the middle of the embedding space, like really are the random errors that I was talking about in my error analysis. So issues with synthetic data, issues with like overlapping issue space. Yes. Sorry. And so we didn't identify any like systematic reason why that was occurring. I think it comes down to the things that I was talking about in the error analysis. Does that answer what?
I think so, yeah. An idea I had proposed is that as a next step, potentially having a second model that's used to distinguish between these overlapping clusters. Would love to hear if anyone else on the call has any thoughts as to potential solutions.
So that would mean basically like if a point is in that middle section of the embedding space, it then goes into another clustering model that's looking more specifically at that area.
I mean, it could just be a, even a binary classification model.
I see.
Yeah. I mean, of course, when you're looking at this in 512 dimensions, it might not, the like center brown area might be further away from, one of the other clusters nearby than it looks on this two-dimensional graph. But yeah, basically using like the benefit of this model's output, and then further segmenting it using a different technique might work.
Mhm. That's a really good point.
I did have a question. This is not so much technical towards the actual data, but I was actually thinking about ways you can actually apply this. And are you guys familiar with maybe any of like the compliance policies in order to actually deploy a model like this within a government? Things such as like auditability, decision transparency, data handling, things like that.
No.
Yeah, I don't think we're really familiar with that.
And
All right, no
this
worries.
was a big reason why we generated a synthetic data set to really like work on the classification aspect of it. I think that was our main focus, but obviously more checks and balances, I guess, would be needed along the way. But I think in order to even conceive of that, you need to like know if it's possible to classify things as you expect them to be
Mhm.
classified. So I think that would be a great next step to kind of maybe rethink certain steps to integrate what you just mentioned.
Yeah. Thank you.
Megan, do you want to comment on any of that, or I can comment on the tech front? Or...
I would not feel comfortable jumping in on the tech front.
Yeah. Oh, I meant in the non-tech front. But yeah, I mean technically Azalkil is probably where, AWS has its own gov cloud, and there are definitely extra security precautions taking place. As the team here mentioned, there's no real constituent data being used in this training. There are security audits. Yeah, there's a lot that goes into that. Actually, I mean, happy to connect after the call with anyone who'd like to chat more about that.
Yeah, that would be great. Thank you.
I'll give it another minute here.
Okay.
Yeah.
I'll ask a question, like a pedagogical question. Like, what part of this did you guys feel was most beneficial to you as this was your capstone project? Like, you guys are about to be out of college and moving on. So, how did the partnership and the internship with Civic most serve you guys moving forward in your academic careers?
I'll go first very briefly. So I feel like throughout the process, we have a lot of exposure in working with professionals, working with sponsors, and we have spent a lot of time collaborating with each other and also presenting our deliverables for you. So my point would be the professional skill that we gain throughout the process.
Yeah, I would agree.
Probably also getting more comfortable with not knowing things and then figuring them out as you go. Because, maybe Julian drops like, oh, you can try doing this feature or like, running this code. And we're like, I've never heard of that before. And then kind of nodding and being like, yes, yes. And then we figured it out. And I think that was great. Just, learning by doing.
Well, I think that a lot of us didn't know what embeddings were at the beginning of this semester, which is silly, but I think it definitely both the professionalism aspect, but also like not to say that we were thrown into the deep end because we had a lot of support from Julian and professors at Smith, but having to prove to ourselves that we could do things that we didn't already know how to do, I think was hugely like beneficial going in, like graduating. That's like a nice thing to have under your belt.
Yep.
Yeah. So thank you for the question. That was nice and reflective.
Okay, well, amazing. Yeah, I just, it looks like Nico dropped, but they can watch on camera, on video later. But yeah, I mean, you guys did obviously like a really amazing job. I've expressed to you before that, the professionalism and just general ability to produce great work is like really at the level of like people who actually like, work in the field. So that was really exciting to be part of on our side. So yeah, great things ahead for everyone here.
Thank you.
Cool. Well, yeah, I'll let everyone go here and hope everyone has a really amazing rest of their day. Happy Hanukkah, Merry Christmas, and have a great New Year season. Thanks, everyone.
Thank you.
Thanks, guys.
So much for listening.
Thanks. Bye.